Hi, my name is Geza Sabo from Ericsson Research, and I would like to speak about radio resource and quality of control-aware planning for self-reconfiguring factory cells. The task that we would like to deal with in this paper is that when the current mass production assembly lines are designed, robots are deployed to repeat a limited set of tasks as accurately and the fast as possible to maximize their productivity and minimize the number of faulty parts. The reprogramming of this robot occurs very rarely, per week or per month basis, and takes a very long time, days or weeks, and it's very difficult task requiring a lot of expertise. We say that there can be some task identified in a robotic cell that needs relaxed requirements, and the whole process can be sped up. We test some of these use cases in a simulator, and also we analyze the radio effects if it's considered this whole setup as a cyber physical production system. We would like to apply part of AI, the planning. Automated planning and scheduling is one of the major fields of artificial intelligence. Planning focuses on realization of strategies or action sequences executed by intelligent agents, autonomous robots, unmanned vehicles. The role of the planning system is to find sequences of actions which lead from the initial state to a given goal. It can be very difficult. Without proper simplification, each of the problem can lead to combinatorial explosion and huge state spaces that needs to be explored somehow. And in this paper, we use some of the common ways to represent planning problems. It's called the PDDL representation, the PDDL language. The use cases that we would like to tackle here is the first one is these are pick and place tasks executed in a robotic cell. It's the robotic cell of the simulation comes from the Area 2018 environment, and we applied ROSHPLAN. ROSHPLAN is a framework which provides a collection of tools for AI planning in a ROS system. ROS stands for Robot Operating System, and it's a very common way among practitioners to apply for research in robotics. Here you can see the architecture of ROSHPLAN. It has been integrated into the Area 2018 competition environment. I would like to show a video on this whole setup. So the baseline that we start from is that there is one industry grade arm in the system. The task here is to put parts from yellow boxes to the shipping boxes. Those are the brown ones going at the conveyor belt. And ROSHPLAN is applied for planning and plan dispatching. In the upper side, you can see how the robot performs the task. In the lower side, it is show how in a Gantt-like diagram what's happening from where to where the robot picks and places stuff in a timely manner. It collects. There is a linear actuator on which the robot can move toward, and the robot simply collects these parts, and while making the shipping boxes ready, and when everything has been finished, the drone picks up the packages to be delivered, and there is a KPI set that is returned by the competition environment. So this is the baseline. And our finding is the application of the conveyor belt is which sounded trivial, but none of the first three contestants of the React 2018 applied adaptive conveyor belt. So it's one advantage of using planning, that it can come out with ideas that was otherwise non-trivial for humans. As a second step, we would like to introduce the concept of modular robotics and the self-reconfiguring robotic cell. So I would like to show this as well in action. So this is a theoretical view how a robotic cell can be self-reconfigure itself. So there are three parts in the very same robotic cell. There are actuators, there are joints, there are parts that can be put together, and it can be possible. So with a modular robotic arm, completely new kind of actions can be executed, which would be otherwise very uncommon with the common industrial setup. So, for example, putting together robotic arm, putting together AGV, joining one on top of the other. What is required for this are self-contained servos that has radio connectivity foremost, and batteries. In this case, there is no cabling in the system, so that kind of assembly with the big robotic arm is possible. The modular robot has some trade-offs. So the trade-off is that compared to the industrial grade arm, the modular arms has more inaccuracy. It's somewhat slower. There is a bigger backlash per servo for heavy, or for the modular or for the modules. And in the planning, we defined some predicates for the goal that it can happen that if not the industrial arm, but modular arms execute the pick and place action, then the precise positioning is not happening. If we check this in the simulator, now in the simulator there are two robotic arms which are assumed to be built. In the simulator there is no collision between the arms, and what you can see here is that they execute in parallel the pick and place actions. So the small ones and the big ones can do putting parts in the shipping box. We implemented with some relaxation of the accurate movement of these arms. So what you can see here is that the parts are moved there if some part of the pull action has been executed. And the interesting part is that after preparing the shipping boxes, with the small arm and with the big arm, at the end of or before finalizing the whole movement or the whole execution, the industrial robotic arm starts to fix the position of the gears that ends up with accurate positioning of the parts in the shipping boxes. If we introduce a radio resource limit into the system, the idea behind this is that there is a significant networking aspect of the robot modules. While the industrial robot arm can be addressed as one entity, meaning that the controller sends out velocity commands containing a vector of 6 for all the joints, the modular robot has to be addressed one by one. And this issue arises for the status messages as well. So why the industrial arm sends out the status packet in every 8 milliseconds containing the positions, force, current, all the joints, the module send the same info one by one. So how we can consider this is we can put this information into the planning and try to consider the radio usage during the planning as well. So we applied some modeling of the radio resource with tokens. Usage of modular arms cost 6 tokens. Usage of an industrial arm cost 1 token. And in this particular use case that is simulated here, we limited the number of available tokens to 10. And the yellow area behind and this chart shows the utilized radio resources. What you can see here is that the level of parallel execution has been decreased somewhat. So currently only one modular arm is used, and but still it has a higher level of parallelism or execution as it was in the baseline case, while the radio resource limit has been considered. My conclusion is that, or I have left out some of the use cases that we touched upon in this paper, and please you can read the rest of it in the paper. The conclusion is that we propose the quality of control over self-reconfiguration, creating factory cell composed of modular robot elements, and we considered radio resources during action planning. They created plans that are executed in the React 2018 environment, and with well-defined actions, the modular robots can speed up and pick and place tasks with relaxed radio resource usage as well.